So let's jump back to this picture here. So we've now taken a look at the CPU, and we've talked about how your computer actually goes about handling instructions and what it means to actually compute something, and the actually kind of complicated process that goes into simply adding two numbers together, let alone reading an email. So now let's talk about your computer's memory. So this can take the form of two forms: this short-term memory of RAM and the long-term memory inside of your hard drive. So let's talk about RAM first. So before we do that, let's just get a sense of these terms that we introduced in the last lecture. But remember, in a byte, or abbreviated B, that's the same as 8 bits. And because that's a really small quantity, we start building things up like this. We have a kilobyte, that's 1,000 bytes, a megabyte, that's 10 to the 6 bytes, a gigabyte, and so on. And so these are just kind of relatively what these quantities actually mean. So in terms of actual storage, let's actually talk about what could be a byte. So how much data is a byte? So what could you store in a single byte, for example? Yeah, so we store 8 bits. So what's something we looked at last week that we could represent using 8 bits? Yeah, so we could use the number 2. Or what if we wanted to represent a letter? How could we represent that from last week? Yeah, so ASCII. So remember, our ASCII table went from 0 to 127. So that's pretty close to 8 bits, or definitely less than 8 bits. So a byte is about the same as storing a single character of text. So how about a kilobyte? Any idea of how large a kilobyte is? What kind of file maybe might take up several kilobytes on your disk? What's that? Yeah, so what type of file is 1,000 bytes, for example? So what might be sitting on your hard drive as you're browsing around and that might occupy 1,000 bytes? Yeah, exactly. So a Word document. So you've probably seen a Word document or a PDF that just has some text. It's probably somewhere in the range of 20 to 30 kilobytes or so. So that's kind of the scale of a kilobyte. How about a megabyte? Yeah, so a big picture from a digital camera, and there's also a song. So not a bad heuristic is about a megabyte per minute. So if you have, 3 megabyte MP3, a 3-minute MP3 song, that's probably about 3 megabytes or so. Same thing with digital camera pictures. Depending on how big it is, a larger picture is obviously going to be many more megabytes than a small picture. So how about gigabytes? What might be gigabytes in size? Yeah, so I heard a bunch of different things. So something like a program, something like Adobe Photoshop, for example. All of the code that powers Adobe Photoshop, all the instructions that are necessary to power Adobe Photoshop, there are probably a lot of them, right? Because Adobe Photoshop is a really complicated program. So the space required to store all of those instructions is on the order of gigabytes in size. So I also heard a video. So the videos that you watch on E1's website are roughly a gigabyte in size. If you get a Blu-ray disc, one of those movies is on the order of 25 gigabytes or so. A standard, like a DVD quality movie, is maybe 4 gigabytes in size. But again, the quality of the movie, just like the quality of a picture, is going to determine how big it is. So a higher resolution movie, like the HD movie on your Blu-ray disc, is going to occupy much more space than just kind of a small movie you downloaded from YouTube. And finally, how about a terabyte? So in terms of, let's say, songs, guesses as to how many songs fit in a terabyte? 1,000, we have 50,000, 50. Are there guesses? So 3,000. So actually, a terabyte is about 250,000 songs, so 250,000. So when you buy one of those computers, an external hard drive that says it has a terabyte of space, it's a lot of space. The reason this being is because we were adding a bunch of zeros between a gigabyte and a terabyte. Every time we add a zero, that's much more than just twice as much, for example. That's a whole lot more storage space. So a terabyte holds a whole lot of data. So this is just kind of a sense of what these words actually mean when we start saying things like RAM is 4 gigabytes. It's like saying RAM can, if you have a movie, you can probably put the whole thing in RAM. But you could not, for example, put 250,000 songs inside of 4 gigabytes. So let's talk about the different forms of storage inside of your computer, kind of in descending order. So let's start with the smallest type of storage. We're going to move up and increase the amount of storage that each of these things has. So it just so happens that generally, the smaller the storage is, the faster it is to access. And a lot of that is actually driven by cost. So if it costs more to make something be able to access faster, in order to produce more of it, it's just going to cost more. So that means that the larger forms of storage are just going to be slower to access. So the smallest form of storage that we have on your computer are these things called registers. And the registers are a really, really small piece of data, or slot for data, actually on the CPU. And so the registers are kind of the working memory of your CPU. If I say I need to add two numbers together, then those two numbers are probably stored on the CPU register. Right? They're kind of, if the CPU is in the middle of something and it needs to do something with some data, immediately it's probably going to be on one of those registers. So similarly, when we stored the result earlier of 5 plus 3, we needed to take that 8 and put it somewhere. We probably put it still on the CPU or a register. So registers are on the order of kilobytes in size, or sorry, even smaller than that, on the order of bytes in size. So typically something like 32 bits would be the size of a single register. So really, really small amount of data, but this is about as fast as it gets in terms of accessing your data, because it's actually right there sitting on your CPU. We don't need to communicate with the motherboard or anything like that. It's just right there. So typically your CPU has some number of registers, maybe 64 or 128, or even smaller than that maybe, but that's just simply not enough, right? We need some larger space for short-term memory. And as we've seen, this is called RAM. So RAM stands for Random Access Memory. And that simply means that it's no faster, for example, to access one piece of RAM, like the RAM on one end of the stick, than it is to access the data stored on the other end of that stick. So we can essentially distribute this data randomly, and we don't have to worry about any performance considerations. So your computer typically has, as we said, between 4 and 8 gigabytes in RAM, and it's used to store data that your programs currently need. So just some short-term data that your program can later throw away as soon as it's terminated, but it just needs some working space. So for example, if you're playing a song, then we might need to put that song in RAM so that we have data to play. And we'll see later in the multimedia lecture more about how audio files and video files work. But in order to allow you to play this song without kind of delays or skipping in the middle of the song, we want to be able to put it in some kind of fast short-term memory. So unfortunately, we can't fit a whole song on a register. It's just not big enough. So instead, we'll resort to RAM, which, because it's larger, is a bit slower than a register. We'll see how slower, exactly how slower later. But it's much faster than accessing something like your hard drive. So that's basically what RAM is used for. The more RAM you have inside of your computer, the more different things you can do at once. Because if you have 4 gigabytes of RAM and you have 2 processes competing for that 4 gigabytes versus 20 processes competing for that 4 gigabytes, you're going to notice that your computer just runs smoother when you just have more available space that your programs can use. So we saw before that a stick of RAM looks something like this. This could be a stick of RAM that's stored in a desktop that looks just like the one that we saw in the motherboard that we took apart yesterday. So if we jump back to my activity monitor, which I will do, we can see here in this right column, we can see how much RAM each process is actually using, so how much memory. If I click here, I can actually sort it, and I can scroll up. I can see that this process here is using 460 megabytes of RAM. So that's about half a gigabyte. And this particular laptop happens to have 8 gigabytes installed. But you can see that if I started running this program a few times, suddenly it's going to be requesting a whole lot of RAM. So that's why having more memory is going to allow me to do more things at the same time, because this has more memory that it can pull from. So the culprit of this is this thing here, which is a kernel task. And we saw before that the kernel, remember, is kind of what interfaces all the communication between the software and the actual hardware. So because that's kind of an important job, it's not too bad that that's taking up a lot of space. But next up, we have Flash Player, which is not only consuming a ton of our CPU, it's also consuming a ton of RAM just to play videos. And down here, this is also Google Chrome. And we've seen that if I start opening up more and more tabs, we've seen that that's going to start more and more processes. And each of these processes now is going to start requesting its own amount of RAM. So we see down here, these 3 here, each of these processes or each of these tabs equivalently is requesting 80, 70 megabytes of RAM. So we can see that more RAM means that I can do more things at the same time. I can have more Google Chrome tabs open, for example. So let's talk about how your computer actually reads and writes data from RAM. So when I say I have 4 gigabytes of RAM, that might be distributed over 2 sticks. So for example, this computer here has 2 different slots for RAM. But as far as your computer is concerned, this is just this big, huge chunk of memory. And this entire big chunk of 4 gigabytes is divided up into really small slots of a byte each. So each of these bytes needs to have some unique address. So as you know, you're driving down a street, each of those houses on the street has a unique address. So if someone tells you, I want you to go to the house at 123 something street, that 123 tells you where on the street you need to go. So similarly, every byte of RAM is going to have some unique address. So that means that when we have 4 gigabytes of RAM, we have that many different addresses or little 1-byte blocks that we can read data from or write data into. So your contents of RAM could look something like this. So again, we're going to consider this 4 gigabytes of RAM, this big, huge block. So this is just one section. And over here on the left, this is a single byte. You can see here because we have 1, 2, 3, 4, 5, 6, 7, 8 bits, which is 1 byte. And this is at the address 100. So that means that this 1-byte block of RAM, we can address it, we can access it using the number 100. That's its address. So the next block here is the next address on this street of RAM. And inside of this, we again have 8 bytes, and they all happen to be zeros. So you can imagine this huge grid of all these little 1-byte blocks. And that is how your computer is actually representing data inside of RAM. So if this is what our RAM could look like, let's see what happens when we want to read something from it. So let's say that we have a number stored at the address 101. And in order to read data from RAM, we need to know how many bits I actually want to read. So let's say, for example, I have a number stored starting at the address 101, and I want to read 32 bits of data, which is just going to be, I'm going to read 4 bytes. So this is what could happen. The CPU says, I want those 32 bits starting at address 101. That means it's going to read all of the 8 bits from address 101. Then it's going to move on to the next address, read those 8 bits, move on to the next address, read those 8 bits, until eventually it's read all 32 bits, or 4 bytes, because each one of these blocks is a single byte. So now we can just combine all these bits into one big, long series of bits that looks something like this. And so now we've actually just taken the data stored in RAM, and now we have this big number. And this representation is called Big-Endian. We basically said if the data starts at address 101, we're just going to read the first 8 bits from 101, then the next 8 bits, my number, will come from 102, and so on. So this is just kind of intuitively how you might read data from RAM. It's just kind of like copying and pasting everything together and making these 8 small chunks into one big chunk that represents a number. So almost counterintuitively, your CPU might actually read data like this. So this is a little bit backwards, but not quite. So your data might be stored in RAM like this. And if we want to read the number that's stored at the same address, rather than saying the first 8 bits come from address 101, we might say the last 8 bits come from address 101. So before we put these bits over here, we put these zeros at the beginning. We're now going to put them at the end. So after we've read all 8 bits in address 101, we're going to move on to the address 102. And again, rather than building the number from left to right, we're going to build the number from right to left. So those next 8 bits are going to be stored here, right to the left of 101. Then the next bits will be stored to the left of that, until we've again read all 32 bits. We've just kind of put them in a different order. So this happens to be called Little-Endian. We're saying that at the smallest address, we're going to put that, instead of at the left of the number, all the way over to the right. So just kind of backwards, but we can still do the same exact thing, is read data from RAM. If this big chunk of memory just has a bunch of bits stored in series, we can just interpret those bits in different ways. So one CPU might say, I want to read left to right, and another CPU might say, I want to build this sequence from right to left. But we're always reading 1 byte at a time. So 2 just different representations of data in RAM. Any questions? Yeah?
So like when we play a song or store that because it's being used at that moment. So does that mean that that file has actually been copied from wherever it originally is, and a copy is made on RAM?
Yeah, exactly. So the question was, so if we're playing a song and suddenly that song goes into RAM, does that mean we're actually copying data from our hard drive where the song is stored into RAM? And that's exactly what we're doing. We'll see that in just a sec. But what we need to do is, rather than saying, I need to get a byte of the song from the hard drive, move that all the way to the CPU, play it, get another byte from the hard drive, put it all to the CPU, and play it, we're going to take the song, we're going to move it into RAM so we can start accessing that much faster. So we're going to copy the data that's on our hard drive into a different source of data, which is our RAM. Oh, yeah?
What if you're playing it like directly from the disk or CD or iPod? It doesn't duplicate it in your hard drive, obviously, right?
Sure. So what if we're instead playing from an iPod or CD? So now it's a different process. So rather than copying the data from the hard drive to RAM, we're probably going to copy the data from the CD into RAM. So something's going to read our CD. It's going to send those bits down along into RAM, and then our CPU can access them much faster. Other question? Yeah?
That is a question about the Big-Endian and Little-Endian processes.
Yeah.
So are certain CPUs configured to read in a certain way, or is it kind of more than arbitrary?
Exactly. So when do we use this Big-Endian representation versus Little-Endian indentation? You're exactly right. CPUs will decide either I will read data in this way, and that's how I'm configured, or I will read data this way, the Little-Endian way. On modern CPUs, Little-Endian is actually a little more common, even though it's a little more counterintuitive as far as we're concerned. So yeah, so this is just how the CPU actually goes about taking this big grid of bits and converting it into a number that it might work with. OK, so what we were just discussing actually is a great segue into this next concept called the cache. So we said that it might be really expensive and time-consuming to read something from the hard drive. And that's just because we said the hard drive has a larger capacity, and so in order to make it fast, it would cost a lot, so we're just going to accept the fact that reading something from the hard drive is a little bit slower. So what we want to do is somehow provide some faster access to that data. So let's take the hard drive out of the picture for just a minute and say that we're reading data from RAM. Compared to the registers on your CPU, it's way slower to read something from RAM than it is to read it directly in the register. And the size difference between a register and RAM is pretty huge, right? We're going from 32 bits to 4 gigabytes. And that's just a massive difference. So it'd be really inefficient to kind of copy things only 32 bits at a time into separate registers if we wanted to do something with them on the CPU. So to kind of mitigate this problem, we have something called the cache. And the cache is this additional layer of storage that sits between your RAM and your CPU. So here we have a stick of RAM. And let's say that we're accessing a lot of data from this RAM. So for example, I have a song on repeat. And that song's on repeat. That means I'm going to need to keep accessing these same bits and bytes over and over and over again. And if we said that if it's expensive for me to go from the CPU, so here, and read data from here, we want to introduce some middleman. And this middleman is kind of in between the RAM and the registers in terms of both size and performance. So here we have something called the cache. And there are different levels. So this is the L2 cache, which means it's kind of level 2. It's slower than the L1 cache, which actually sits right here on the CPU. But the L2 cache is going to hold more data than the L1 cache. So the process of actually reading something from RAM might not look like take data from RAM and read it directly into the CPU. What we might instead do is say, OK, I'm playing this song on repeat. I'm going to take this song, I'm going to take it from RAM, and I'm going to put it on the cache. Now, the cache is much faster to access than just the CPU. So now I can play the song more efficiently, because I don't need to go all the way to RAM. I can just go to the cache, which is smaller. We're talking on the order of several megabytes, maybe. The L1 cache might be smaller than the L2 cache. There could be an L3 cache, which is even larger. But it's smaller than RAM, but much larger than a register. And so this is just kind of this place where we can temporarily put something, we can cache it, so that we can access it more quickly later. So let's quickly talk about an analogy. So for example, if I'm cooking something, I'm in my kitchen, and at any given time, I have 2 hands. I can have a knife in one hand, and I can have a vegetable in the other hand. So if I want to access something like a tomato, it doesn't get much faster than me actually holding the tomato, right? It's already right there, and I have it. But I only have 2 hands, and that means I can't really hold that much at once. So what I might instead do is if I know I'm going to be making a salad, might go and get all of my vegetables from my counter or from my kitchen and put them wherever I'm cutting, so on the cutting board. So the cutting board is kind of like the cache. I know that I'm going to be accessing all of these vegetables pretty frequently, but I can't hold them all at once. So I need to move them to some placer that's much quicker for me to access. Right? If I need to go all the way to the cupboard or wherever, fridge, I probably don't want to put vegetables in the cupboard. So if I need to go all the way to the fridge to get my vegetable every single time, it's just going to be really inefficient. Right? I have all this counter space. Why don't I just put my vegetables there where I can access them faster? So this is kind of the role of the cache. I don't have to have the cache. It just makes my life a lot easier because I have this extra space where I can put stuff where it's more easily accessible. Right? In the worst case, if I realize I forgot to grab lettuce, I can drive all the way to the grocery store, but that's probably not the best idea to do every single time I need lettuce. So the cache is just this extra layer of storage where I can put things and access them more quickly, but I just don't have as much space. So any questions on caching as a concept? So as I said before, we're actually going to be copying data. So data will live on RAM. We're going to copy that data onto the cache. So that means that when you're playing a song, the song could live on your hard drive, then some of it could live in your RAM, then even a smaller amount might live in your cache, and an even smaller amount is going to be duplicated on your CPU. So duplicated across all of these places, but we need to do that in order to access it more efficiently. So caching is something that we'll see again and again throughout this course. Once you look at networking, this is going to come up again. Because this isn't really something that's just specific to CPUs. This is more of a general computing concept and a way to take tasks and make them more efficient.